Chapter 11 adds reflections and transparency to the ray tracer, and it's a difficult chapter to get through. The material class is updated to include reflectivity, which is going to be a value between 0 and 1. When a ray strikes a reflective surface, we need to calculate the vector that is reflected off of it. This vector will fly off into our scene and hopefully strike some other object, and that's going to show up in our reflection. The computations class will store a reflect vector, calculated using the normal of the surface and the incoming vector. The reflected color method, which is part of the scene class, will return a black value when there is nothing to reflect, such as when an object's reflectivity is set to 0. If a reflection is part of the material, then the overpoint will be used so that we don't have self-reflections on the surface due to all that floating point nonsense. The color at method is then called, and with the reflection ray, will continue to bounce around until there's either no intersection with anything, or we strike a non-reflective surface which will then return to us a color. In this test, we're setting up a default scene where we're calculating the color of a ray reflected off of a planar surface below the nested spheres that we have, along with a light source. Shade hit is now updated to account for reflected objects. I need to do this outside the light accumulation loop that I have to handle multiple lights in the scene, and I then add this reflected color to the surface color. If we have two perfect mirrors pointed at one another, a ray will bounce between them potentially forever, but as our calculations go to infinity, our computer is going to eventually run out of memory. Therefore, we need to limit the amount of recursion we allow in the program. If we use a counter as the maximum limit on the number of bounces we can have, well, that's one way of solving the problem. With each subsequent bounce, the counter will decrease until we get to 0, where we'll return a value of black and stop reflecting. This counter gets passed through the different methods handling color calculations and is reduced each time. With transparency comes a refraction index as part of the object's material. This is what causes a pencil to appear bent when you place it within a glass cup full of water. When the light moves from a medium with one refractive index to a different one, it gets bent. A transparency variable is also added to the material, which is a little counterintuitive for me. From real-time rendering, I'm used to 1.0 or white being opaque and 0.0 or black being transparent, while this rate uses the opposite. The next test is a bit confusing at first if you just look at the code, so let's pause for a second and understand what the book is having us do. The test involves 3 spheres, with 2 nested inside a larger one, and those 2 slightly intersecting. Each sphere has a different refractive index. How the light bends is based on both the exterior medium and the interior medium's value. We call these N1 and N2 respectively. When evaluating a transparent object, we not only pass in where the ray struck the surface, but the entire list of intersections that were saved from earlier. This is a reason why we just didn't throw them all away in our calculations. I'm going to leave the overall algorithm to the book, but simply put, we are stepping through the list and calculating our N1 and N2 values. The computations class has the term N1 and N2 added, so we know the refractive index the hit is coming from and going into. The prepare method also has the entire list of intersections now passed into it. I have to add a new parameter for this intersection list and set that to null by default so that any previous usage of the prepare method doesn't throw any errors. I was using a default refractive index of air for my materials. I should have been using a vacuum like the book expects, which was throwing off my answers. I'm still failing my unit tests, so I stepped through using debugging, and after a short time studying the output, I've noticed that I test against the wrong object. My variable names and the books are a bit at odds with one another. I changed to using the intersections list object rather than the object that was hit by the ray, and things now start working just fine. The underpoint is just like the overpoint, except underneath the surface, and is used in transparency to make sure we don't have any self-intersections again due to floating point error. A new method called refracted color is created in the scene class to handle calculating the color of the refraction component. If an object has no transparency, then no refraction is calculated and the color black is returned. Since black's RGB value is 000, it's going to have no effect on the final summed color value calculated. Just like reflections, we're going to need to worry about the maximum recursion depth and limit the number of refractions based on an integer counter variable. An interesting thing that happened when moving from a medium of high refractive index to that of a lower refractive index is that the ray can bounce off the surface and experience total internal reflection. When this happens, there's no refraction through the material and the color return should be black. Finally, we get to the point where we're going to test calculate the refracted color of a surface. The test sets the ambient component of the material to 1 so that lighting isn't part of the result and we don't have to worry about it. And we also set a test pattern so that the value that gets returned is just the transformed point into pattern coordinates. However, since the patterns matrix is the identity matrix, it's not going to affect the output at all. Time to integrate refraction into the overall shade hit method, which will now sum the lighting, reflection, and refraction components. But see, the book has a catch, and that is the Fresnel effect. Reflections are actually stronger at a glancing angle than when viewed directly perpendicular to a surface. You can even see this yourself in a surface of a desk. If you look at it straight on, you don't see much reflection, but if you lower yourself nearly parallel to the surface, you'll start to see a reflection of everything around you. Of course, this does depend on how rough your desk surface is. The book states that this is actually a complex topic, but there was an approximation made by Christoph Schlick that works for us. To implement this, the book has us make 4 unit tests. I'm going to admit here, I'm not too knowledgeable in this area, so I used the book's implementation and didn't ask too many questions. That's something I'm going to investigate another day. I'm having some difficulty getting the tests to pass, and I don't see anything wrong with my values or equations. I checked the errata online, but don't see anything for the section I'm currently working on. So I continue onward with the final test implementation and hope things fall into place. Interestingly, I passed the final test, but not the two before it. I decide to ignore it and create an image to see reflection and transparency in action. I start by copying the elements from the previous chapter's scene to speed things up. I add values for the new material parameters of transparency, refraction, and reflection. However, my output completely ignores all of my recent additions. So I start stripping away from my world to simplify things, leaving only reflection. Well, transparency seems to be broken. I go back and repeat all prior unit tests to check for any mistakes. I'm checking that my material values actually got set and didn't mess something up in my getters and setter methods. I rename my variables just to make sense of things a bit more when combining elements. And the investigation continues. Nothing found yet. I remove the default null value for a moment on intersections, just to see whether or not I'm missing it someplace. This causes me to go back and refactor all of my old code. I cut the scene down to a single sphere to eliminate even more variables, and then to reduce time rendering, make the output image very small, and start manually walking through as I debug the entire process pixel by pixel. I decide finally to just bring in a background object to see if any transparency is happening, and what would you know, there it is. The checkerboard showing up through the object. I'm really not sure what I did to change things, or if there was just something odd going on with my scene, and simplifying things fixed the issue. Now I'm playing around with different values to see if things are actually working, or if this whole thing has just been some sort of a fluke. Now it's time to slowly make the scene more complex again, bringing back the floor with a pattern. Now I read ahead a little bit and saw that the final challenge in the chapter is to make a transparent, water-like surface above a bunch of objects that are supposed to be stones. The problem is with our current shadow algorithm, everything below the water plane is going to be in shadow, which isn't how water should behave. Therefore, I decide that if I add a Boolean parameter to the ray object that controls whether shadows can be cast or received on a per object basis, I can make the scene work. And now I can control shadow casting on a per object level. And now it's time for the chapter underwater challenge. Now if you've looked at the timeline on this video, you'll notice we're not quite to the end. And that's because I've decided to add a few new features that are not in the book. I want to have lots of randomized spheres on the sea floor with different positions and colors, but I don't want to manually enter in all that information. I'm going to use randomization methods in the color and point class to generate everything for me. I'm going to put bounds on the point class randomizer to have a start and end value so that points will be only generated within a rectangle of space. Unfortunately, with every test I perform, the world seems to be coming out completely black, and rendering in only a few seconds. Does that sound familiar yet? Yeah, I once again forgot to put in a light source. Once I notice this, I'm going to go back in and add a quick console line that warns me whenever I try to render without a light in the scene, so this never happens again. And there is a sphere, half under the water. But where are my 40 spheres in different places with different colors? I've actually made a huge mistake. If you create random objects and make calls incredibly quickly in succession like I am doing here, you're likely to get the same value over and over again. This is why my objects are in the same position and don't have much variation at all. To fix this, I need to create a global random class instance that I will be pulling from that is project-wide. As I do this, I'll end up making a few other smaller changes, including taking the constants out of my utility class and putting them in their own constants class. I also added some new overloaded methods to my matrix creation that allows me to pass in vectors and points instead of just using floating x, y, and z values to create translate and scale matrices. One issue is that I'm using static methods. However, I really need to use instance methods instead. This causes me to rewrite how things work. In my random class, at its initial creation, it makes the system.random instance that I'll be pulling values from. Everything in my ray tracer will then be using my personal random class to make sure I am pulling new subsequent random values. Now all my objects appear to have the same value. Why is that? Once again, I messed up and have all the objects actually sharing the same color reference. So when it changes for one material, it actually changes for all of them. Making sure that they all have a unique reference solves the problem, but not after considerable head scratching on my part and some manual debugging. And that's my final scene. A water plane, ground plane, and stones scattered about with random locations and colors. Things look a little odd because we're simulating refraction, which most game engines actually don't do. Kinda looks weird when you see it here. This was a challenging chapter to get through, but I think things will get easier in chapter 12, where all we're doing is adding cubes as new primitive objects. We're well over halfway through the book, and the end is starting to be within sight.